Hi, my name is Rohan Chaudhary, and I recently earned my Master of Science in Computer Science degree from Texas A&M University, College Station. Today, I'm excited to discuss our research titled DACL, Disfluency Augmented Curriculum Learning for Fluent Text Generation, which has been accepted at the 2024 Joint International Conference on Computational Linguistics, Language Resources and Evaluation, also known as LREC-COLING 2024. I'd also like to express my gratitude to my collaborators in this work, Maria Teleki and Shangzhuo Dong, both PhD students at Texas A&M, and Professor James Cavalli from the Department of Computer Science and Engineering at Texas A&M University. Thank you all for joining us in this session. Here, I'm going to start with a 1-minute summary of our research before going into the details. In this work, we basically aim at disfluency removal from transcribed spoken text. Now, what are disfluencies? Disfluencies are any breaks in the regular flow of speech, such as false starts, corrections, repeats, and fill pauses. In the sentence shown here, the first kind of invasion of the first type of privacy seemed invaded to me. The referendum and interregnum parts outlined here consist of the disfluent parts of the sentence. Excluding them, we get the fluent part, that is the first type of privacy seemed invaded to me. For the task of disfluency removal, we prefer having less false positives than less false negatives. That is, we do not want to remove important information at the cost of removing most disfluencies in the text. This also translates to us wanting more precision than more recall for this task. Our model should learn to precisely identify disfluent patterns from given sentences and be able to better generate fluent text from disfluent text. To tackle this, we propose an approach called Disfluency Augmented Curriculum Learning. In short, we call it DACL, which tackles the complex structure of disfluent sentences and generates fluent text from them. In DACL, we first synthetically create text with various levels of disfluency from clean sentences. DACL harnesses this tiered structure for generated synthetic disfluent data using curriculum learning by training the model on basic samples, that is more fluent samples first, before training it on more complex samples, that is more disfluent. Our model surpasses existing techniques in word-based precision by up to 1% and has shown favorable recall and F1 scores on the widely used switchboard Penn Treebank 3 dataset. Now I'll go into the details of our work. Disfluencies are any breaks in the regular flow of speech. Schreiber defines 3 different distinct parts of speech disfluency referred to as referendum, the interregnum, and the repair. According to Liu et al., in the switchboard treebank corpus, which is a standard corpus for parsing studies on conversational speech, the referendum and interregnum parts of the disfluent sentences, which are the disfluent parts of the sentence, are dominated by edited INTJ and PIN nodes. Hence, by identifying and removing these nodes from the sentences, we can obtain the fluent part of the sentence, as shown here. Now, in this task, we would prefer having less false positives than less false negatives. That is, we do not want to remove important information at the cost of removing most of the disfluencies in the text, which also translates to us wanting more precision than more recall. Now, for experimental setup, we use T5 base, which was developed by Google AI as our backbone model. It has 220 million parameters, making it a medium-sized model as compared to recent large language models such as Llama variants and ChatGPT. We use 2 types of datasets, pre-training dataset and evaluation dataset. Pre-training datasets are used to perform the DACL procedure, and we carefully select 2 different types of pre-training dataset. The first is the Spotify podcast dataset, which is comprised of over 100,000 podcasts. The podcasts were transcribed using Google's automatic speech recognition tool. Since the dataset consists of transcribed spoken text, we consider it to be in domain with our evaluation dataset, switchboard treebank corpus, which is also transcribed spoken text. The second pre-training dataset is the Wikisplit dataset, which consists of 1 million English sentences extracted from Wikipedia edits. These sentences are written text and completely devoid of disfluencies, hence considered to be out of domain with our evaluation dataset. We then use the switchboard treebank corpus as our evaluation dataset, which is a standard corpus for parsing studies on conversational speech. Evaluating on the switchboard treebank test set allows us to directly compare our results with previous research work in this domain. We compared the word-based precision recall and F1 scores and root scores of the model at different stages for the task of disfluency removal. Our motivation is to increase the word-based precision scores while also maintaining favorable recall, F1 and root scores. Now, in this work, we address 2 research questions. First question is, how will DACL perform with curriculum learning on in-domain datasets? To address that, we build a synthetic disfluency augmentation approach that produces progressive versions of the original in-domain text or Spotify dataset with various degrees of disfluencies. We then use curriculum learning using the augmented dataset to train a T5-based model for the task of disfluency removal. Second question is, how will DACL perform with the curriculum learning on out-of-domain datasets? To address this, we employ the same methodology as in research question 1. The only difference being we substitute in-domain text with out-of-domain text of the Wikisplit dataset to create synthetically augmented dataset for the rest of the curriculum learning process. Now, as for our process, we train a sequence-to-sequence generation model incrementally on increasing levels of augmented disfluencies. This process is known as curriculum learning, and this increases the model's ability to better identify disfluencies from normal fluent text by facilitating gradual learning and incrementally increasing the generation capability and robustness of the model to disfluencies. We do 3 different kinds of disfluency augmentations, which are repeats, which are just we repeat some words. Interjections. Interjection words are any word from this list of given words. And false starts, which are just edited phrases. For repeats, we sample from a normal distribution to determine the positions in the text to repeat the last term n times. For example, here in this sentence, I am so tired today, with n equals to 3 repeat augmentation, it would become I'm so tired today. For interjections, we similarly sample from a normal distribution to determine the position in the text to inject n uniformly randomly selected interjections from the interjection list, which is well, like, so, okay, you know, I mean. For example, here in this sentence, with n equals 3 interjection augmentation, the sentence may become I am well, so tired today. For false starts, out of the sentences with word length greater than equal to 4, we non-uniformly sample sentences with 80% probability to get a false start repeated n times in it. False starts are considered as the first 2 words of the sentences being repeated n times consecutively for our work. For example, here in the sentence, for n equals to 3 false start augmentation, the sentence may become I'm so tired today. Now, curriculum learning is a method where a machine learning model is trained on simpler data first before moving on to more complex data, mimicking the way human education curricula are structured, as shown here. For our curriculum learning process used in DACL, there are 6 stages. In the first stage, we feed the non-augmented sentences with n equals to 0 level augmentations into the T5 base model and ask it to generate these sentences exactly as they are. This stage enables the model to recognize that if the provided sentences are free from disfluencies, they should be returned unaltered. Consequently, this helps prevent the model from returning unintended random outputs or empty strings as witnessed in some of our ablation studies. From the second stage, we begin introducing some synthetic disfluencies in our input text. We start with a repeat augmented dataset, as it's relatively more straightforward compared to the other augmented datasets. Our input texts are repeat dataset with level n equals to 1 augmentation, and outputs are the original non-augmented sentences. For every stage, we train the best model obtained from the previous stage with the least validation loss on the training set of the pairs of inputs and outputs for that particular stage. In the third stage, our input text becomes repeat augmented dataset with level n equals to 5 augmentation, and the outputs are the same unaltered text before. We are increasing the difficulty of augmentations with every corresponding stage. In the fourth stage, our input text becomes repeat augmentation dataset with level n equals to 10 augmentation, and outputs are the same unaltered text as before. In the fifth stage, our input text become interjection augmented dataset with level n equals to 10 augmentation, and the outputs are set as the original non-augmented texts. Since interjections are easier than false starts, we provide interjections. We show the model interjections first before going into the false starts. In the sixth and final stage of DACL process, our input texts are false starts augmented dataset with level n equals to 10 augmentation, and the outputs are set as the original non-augmented text. After the sixth stage, we take the model with the lowest validation loss and we name it DACL best and proceed to fine-tune it on the target dataset. Now, fine-tuning on the target dataset. Through the DACL process, we obtain the DACL best model that understands the basic of what is a disfluency and can precisely remove disfluencies that we have shown through our synthetic augmentations. However, naturally disfluent datasets like Switchboard Treebank 3 can have more kinds of disfluencies that we have not engineered in our augmentations. To tackle these new types of disfluencies, we fine-tune DACL best, the best checkpoint from DACL, on the training set of the evaluation dataset, that is the Switchboard Treebank corpus. This table here shows the scores after evaluating the respective models on the Switchboard test set for our research question 1 with DACL done on Spotify dataset. The highlighted section in red shows the models trained with different levels of augmented datasets shuffled together without any curriculum learning. These models exhibit low precision, as you can see here, but relatively high recall scores as they return empty strings and random tokens. Now we perform curriculum learning. Now as we perform curriculum learning, we see the scores gradually increasing. Here the recall is initially low, but gradually increases, showing its ability to understand disfluencies better with each step, and the precision consistently is also considerably high and increases. This ablation study shows the importance of intermediate steps in the curriculum learning process. The scores from the row outlined in blue has 2 additional steps of curriculum learning and shows much better scores than the row outlined in red. DACL best is obtained after going through all the stages of the curriculum learning process as outlined here. This model has the highest root scores and decent precision recall and F1 scores. This indicates that the curriculum learning process is instrumental in increasing the quality of the generated outputs. Now this table shows the results of fine-tuning on the switchboard training set and evaluating on the switchboard test set. Directly fine-tuning T5 based on switchboard yields decent scores. However, the model suffers from returning empty strings in few cases, as shown in the red outline section. After fine-tuning DACL best on the switchboard training set, this is the model obtained with the least validation loss on the switchboard validation set and has the highest precision. The training process converges in 14 epochs. This is the result of overfitting the model on the switchboard training set till 66 epochs. It has the highest recall, F1, and root scores, as outlined in the red section. This table shows comparison with previous research. Model with best validation loss has the highest precision, but overfitted model has overall best scores. Overall better scores. However, as the model was overfitting on the training set, it started to identify more and more words and phrases as disfluencies at the cost of precision. We should note that reference texts were human annotated, thus implying that what might appear disfluent to the annotators might not appear disfluent to others, and we risk losing important information. Some examples of this are presented in the paper as well. Now we move on to research question 2. How will DACL perform with curriculum learning on out-of-domain datasets, which is the Wikisplit dataset? This table shows the results of fine-tuning the T5 base model on the Wikisplit training set and testing on the switchboard test set. The scores obtained for DACL best here are lower than the scores obtained for DACL best on Spotify. However, the same trend of score increase is followed in the subsequent curriculum learning stages here as well. This table shows the results of finding the Wikisplit DACL best model on the switchboard training set and testing on the switchboard test set. Clearly, curriculum learning on Spotify, that is in-domain dataset, gives better results than curriculum learning on Wikisplit dataset, that is out-of-domain dataset. Why is that so? So this can be attributed to the fact that Wikisplit is a written dataset that has almost zero speech-related disfluencies, where Spotify is a spoken transcribed dataset that has minimal disfluencies present in the non-augmented datasets. This presence of minimal speech disfluencies in the Spotify dataset adds some noise to the entire training process and also instructs the model to better identify only the repeats, interjections, and false start disfluencies from the sentences and leave the rest unaltered. This makes the model more precise and judicious in its disfluency selection process. Now to conclude, our experiments and ablation studies shows the efficacy of our DACL process, and our best model outperforms the state-of-the-art methods in word-based precision and demonstrates favorable word-based recall and F1 scores on the widely used switchboard test set for the task of disfluency removal. We also find that performing DACL on in-domain test set results in the best precision and favorable recall and F1 scores for the task of disfluency removal, and the scores are better than DACL on out-of-domain datasets. This is the QR code to our GitHub repo. You can scan this QR code to visit our codebase for this work on GitHub. Thank you so much for joining this talk. Please reach out if you have any questions regarding this work, and we will be very happy to help. Thank you.